the problem gives us a spring that is hanging from the ceiling, and the rest length is L. The Once you put a mass of M, the spring stretches up to 2L, reference to the ceiling. The other part of the problem we're gonna discuss later. So let's just calculate the spring constant based on this. So if we look at the drawing, we have a force of gravity and the force here. So since it's at rest, the sum of all the forces must be equal to 0. So mg minus ks delta x equals to 0. Here I'm assuming that the positive coordinate is downwards. Okay. Now, with all this information, we can say k delta x, I'm flipping them so that it's easier to read later, and k equals mg over delta x. And delta x is the change. So we landed at 2L and started at L, right? So we ended up at 2L, started at L, so this is L. That means that the spring constant is mg over L. So now we have a spring constant. Now, let's discuss the second part of the problem. The second part of the problem gives us the spring, and we're going to put more mass at the end, but we're going to put it along the position of the spring, not at the end. So that is effectively cutting off the spring. So if I have a spring that is stretched, so imagine this spring stretched. So let's say this is the rest position. The new position is changed by a factor of delta x. So if I now imagine cutting the spring, then in order to reach, so let's say I cut the spring somewhere, so I make it smaller like this. Oh, that's actually pretty close. So like that. In order to reach the same delta, this delta x, like in order for the spring to get up to this point, each node of the spring would need to stretch more. So compared to this one, assuming it's the same spring and you just cut it. And the spring force is actually given by the material properties of the spring and the tensile strength of the material itself. And so if you need to stretch the material more, you'll have more force. Therefore, you anticipate that the spring force is actually stronger as you cut the spring, because each node would have to stretch more than the previous one by stretching the same amount. And it just happens to be that if you look at this further, then the spring force or the spring constant for that same amount of stretching, so this is the uncut, sorry, so you have the cut spring equals the the spring constant of the uncut divided by a factor that where I'm going to call R, which is the fraction that of the initial spring. So now that we know that, let's tackle the other problem. So the other problem wants us to put a spring somewhere there, and I'm going to call this XR, which is a fraction of the initial size, given what we know of the change of the spring. It's useful to put it in fractions of the initial length. And since this is the original spring, this distance is L, so this distance is L minus XR, or L minus, which equals this. Okay? So, and we're going to put a 2m mass here. So now the forces which is this, the same balance of equations. It just changes that now we have 2mg minus k cut delta x. Okay, so I'm gonna flip that again. So this term I'm gonna put first, the cut one, delta x equals 2mg. And I'm gonna make some notes in this corner. The cut one, we said that it was the uncut one divided by r. This is a bigger, and r is a fraction, so it just goes from 0 to 1. And delta x is where we landed at in the spring. So once you put the mass, how much this stretched. So it'll be, let's say, this distance x minus the rest position, which now is xr. Okay? So putting all that together, we have that is mg over L, all that divided by r. So this is this, because the uncut is mg over L, times x minus xr is 2mg. So if we multiply by mglr, for the other side we have x minus xr equals 2lr. And xr, we said that it was this. So therefore x equals 3rl. Okay? So this is the new position of the spring once you put the 2m mass. Now we want that stretched position to be equal to the other end of the spring, which we said is L times 1 minus R. So that means that 3RL equals L R minus 1. We can factor out this L variable. So we have 3R equals, I flipped it, sorry, 1 minus R. That's shown there. 1 minus R. And therefore, R equals 1/4. So this is the fraction, but we were asked what's the position that we need to put it. So we would just need to, since XR is the actual position, we would replace 1/4 L. So that's the position that we would need to put the mass in order for this stretch distance to be the same as this distance. And that was all. Thank you.